Hi everyone. Today we will discuss backpropagation, which is an algorithm that can be used to train feed-forward neural networks, such as multilayer perceptrons or convolutional neural networks. With some modifications, they can also be used to train recurrent neural networks as well. I will introduce our notation on this two-layer neural network, but we will derive the details of the backpropagation algorithm for an arbitrary and general multilayer perceptron. Let x1 denote our input. It has n plus 1 components, x0, x1, x2, and so on, xn. The first one, x0, is just a constant one, and it is called the bias input. The next n, x1, x2, and so on, xn, are regular inputs to the neural network. In the first layer, we have 3 neurons. After the first step, these neurons calculate the linear combinations of the n plus 1 dimensional input vector x. We use matrix W1 to denote these linear coefficients. The size of W1 is 3 times n plus 1 because it gets an n plus 1 dimensional input and then creates a 3-dimensional output. The linear combinations of this n plus 1 dimensional input vector x with the weight matrix W1 is just S1, which is W1 times x1. In this case, S1 is a 3-dimensional vector. Its components are S11, S12, and S13. After we calculated the linear combinations of the inputs, these quantities go through nonlinear activation functions, which are denoted by SGMs here. The outputs of these activation functions will be the outputs of the neurons in the first layer. They are denoted by y hat 1. Y hat 1 in this case, again, is a 3-dimensional vector because we have 3 neurons. The components of y hat 1, that is the outputs of the 3 neurons in the first layer, are denoted by y hat 1, 1, y hat 1, 2, and y hat 1, 3. This is how we calculate the activations of the 3 neurons in the first layer. After this, we repeat the whole process to calculate the activations of the neurons on the second layer. The activations of these 3 neurons on the first layer will be the inputs of the neurons in the second layer. We write this input of the second layer as x2. Obviously, x2 equals y hat 1 because x2, the input of the second layer, is the same as the output of the first layer. Again, we will have an extra bias input in the second layer. That's denoted with x2, 0, and it's again is just a constant one. Let's assume we have 2 neurons on the second layer, and this second layer will be the output layer of this neural network. First, the neurons of the second layer will calculate the linear combinations of their inputs, that is, the linear combinations of x2. The coefficients of this linear combination are denoted by W2. The size of matrix W2 in this case is 2 times 4, because we have 2 neurons in the second layer, and these neurons get inputs from the 3 neurons on the first layer, plus the constant bias. These linear combinations are denoted by S2, and of course, S2 equals W2 times X2. The components of S2 are denoted by S21 and S2, 2. After we calculated S2, these quantities again go through these nonlinear activation functions, SGM, and then they produce the outputs of the neural network. The outputs of the neurons on the second layer are denoted by y hat 2, 1 and y hat 2, 2. Since this is the last layer of the neural network, often we will just use the notation y hat for the activations of the neurons on this last layer. The components of this y hat are just y hat 1 and y hat 2. Now that we calculated the activations of the neurons on this last layer, we can compare them with the true labels y1 and y2. The difference between the true labels y1 and y2 and the activations of the neurons y hat 1 and y hat 2 in this layer are denoted by epsilon 1 and epsilon 2. So epsilon 1 is y1 minus y hat 1 and epsilon 2 is y2 minus y hat 2. The weights of the neural networks are w1 and w2. When we train a neural network, our goal is to tune these weights such that the errors, epsilon 1 and epsilon 2, are as small as possible on the training set. To train this neural network, we will use the gradient descent method. Generally, the gradient descent method is an algorithm for minimizing a function f in an n-dimensional Euclidean space. So formally, our goal is to find a point x star in this n-dimensional space such that f of x star is the minimum of function f. We assume that f is a differentiable function. If the parameters are set correctly, then the gradient descent algorithm can find a local optimum point of this function f. The gradient descent algorithm works like this. You choose an initial starting point x0 in this n-dimensional Euclidean space, and you also choose a schedule of learning rates tk, which are non-negative numbers. At iteration k, the next point xk equals xk minus 1, the point in the previous iteration, minus the learning rate tk times the gradient of function f at the point xk minus 1. Again, we will use this gradient descent algorithm to optimize the weights of the neural network. If function f is strictly convex and the learning rates are set appropriately, then the gradient descent algorithm will converge to the same point independently from the starting point. Here you can see 5 different starting points, and you can also see that the gradient descent algorithm indeed converged to the same point independently of where the starting points were. However, if the function f is not convex, then depending on the starting points, you might converge to different local minimum points or saddle points. Or in some cases, you might not converge at all. The gradient descent algorithm is sensitive to the learning rate parameter. If it's set to be too big, then the gradient descent algorithm might not even converge. For example, if it's set to be too big, then even if the function f is a convex function, the gradient descent algorithm might not even converge. For example here, if at each iteration k, the learning rate tk is set to a large constant number, and f of x is just this quadratic function here, then as you can see, the gradient descent algorithm is not even converging. We started the algorithm from the starting point x0, And as you can see, as we increase the iteration number, the algorithm is jumping bigger and bigger steps. On the other hand, if the learning rate is too small, then the algorithm might converge too slowly. Here we use the same function f, but the learning rate was set to a smaller number. As you can see, even after 100 iterations, we are still very far from the optimum point. Now we are ready to start discussing the details of the backpropagation algorithm. Matrix W will denote the weight parameters of the neural network. In particular, at time step k of the gradient descent method, the strength of the connection between neuron J on layer L-1 and neuron I on layer L is denoted by WLIJK. For example, on the first layer, this connection between input 0 and neuron 1 is denoted by W110. Similarly, this connection on the first layer between input n and neuron 1 is denoted by W11n. The connection between the 0th input and the third neuron on layer 1 is denoted by W130. And just a last example, the connection between the nth input and the third neuron on layer 1 is denoted by W13n. In this specific example, we have two neurons on the output layer, and the outputs of this neural network are denoted by y-hat1 and y-hat2. The true labels are denoted with y1 and y2. The prediction error of the neural network is epsilon1 and epsilon2. Epsilon1 is just y-hat1 minus y1, and epsilon2 is y-hat2 minus y2. Our goal is to minimize epsilon1 squared plus epsilon2 squared. More generally, we can have NL neurons on the last layer. The outputs of the neurons in this last layer are denoted by y-hat1, y-hat2, y-hat-p, and so on, y-hat and L. We will need to minimize the sum of y-hat-p minus y-p squared, where p is running from 1 to NL. To be able to use gradient descent, we will need to calculate the derivatives of epsilon squared with respect to the parameters of the neural network WLIJ for all layers L and neurons I and J. SLIK denote the summed input of neuron I on layer L before applying the activation function f at time step k. I'm illustrating this on our example multilayer perceptron. Here we can calculate S11, S12, and S13 as the linear combinations of the inputs of the first layer. XLK denotes the input of layer L at time step k, and let y-hat-lk denote the outputs of layer L at time step k. Here you can see the inputs of layer 1 and the outputs of layer 1. The outputs of layer 1 are denoted by y hat 1, 1, y hat 1, 2, and y hat 1, 3. We will use n1, n2, and so on, and L to denote the number of neurons on layers 1, 2, and so on, L. In this example, we have 3 neurons on layer 1 and 2 neurons on layer 2. To be able to proceed, we need to make some simple observations. The first one is that xl equals y hat l minus 1. This is obvious because it just says that the input of layer L is the same as the output of layer L minus 1. This is what I'm showing here for the second layer. The input of the second layer is the same as the output of the first layer. You can also see that SLI is just the linear combination of XLJ quantities with weights WLIJ. This is obvious because this was exactly the definition of SLI, which is just the summed inputs of neuron I on layer L. By definition, XLJ quantities are the inputs of the neurons on layer L, and it is the same as the output of the J's neuron on layer L-1, which is y hat L-1j. Again, by definition, we know that we get y hat by applying the activation function f on its linearly weighted inputs s L-1j. If we just use this observation by changing L to L plus 1, then we get this equation here. I'm visualizing this observation here, showing how we can get S21 and S22 from S11, S12, and S13. Now that we are done with all the preparations, let's introduce the so-called backpropagated error. This is denoted by this delta Lik quantity. We will need to calculate the derivative of the squared error with respect to the weights of the neural network. Here instead, we calculate the derivative of the squared error with respect to the SLI quantities. Since we have NL neurons on the last layer, and the squared error epsilon is just the sum of epsilon p squared, where p is running from 1 to NL, we need to calculate the derivative of this quantity with respect to SLI. So the backpropagated error is defined by this expression. As a special case, we have that on the very last layer, L, the backpropagated error equals this quantity here. By definition, we know that the backpropagated error on the last else layer is this quantity, but epsilon p is just yp minus y hat p. So we need to calculate the derivative of the sum of yp minus y hat p squared with respect to SLI. We know that the derivative of x squared is just 2 times x. Therefore, the derivative here is just 2 times epsilon times the derivative of epsilon with respect to SIL, and this is just the derivative of f at location SLIK because yp is constant in SLI. In what follows, we will need the chain rule. This chain rule says that the derivative of fgh is just the derivative of f with respect to g multiplied with the derivative of g with respect to x plus the derivative of f with respect to h multiplied by the derivative of h with respect to x. We will use this rule in the next steps when we derive the backpropagation algorithm. Finally, we are ready to state the following lemma. This lemma claims that the backpropagated error delta Lik can be calculated recursively from the backpropagated errors on the next layer L plus 1. We will prove this lemma now. We already calculated delta Li on the very last layer, and it was this expression here. This is the definition of delta L minus 1, is the derivative of the squared error with respect to SI L minus 1. And now, using the chain rule, we can see that to calculate this expression, we just need to calculate the derivative of the squared errors with respect to S on layer L and multiply this with the derivative of S on layer L with respect to S on layer L minus 1. Similarly, we can use the same chain rule for any other layers L, and the backpropagated errors can be calculated by this expression. So this is just the definition of the backpropagated error on layer L, and then the chain rule says that we just need to calculate the derivative of the squared error with respect to S on layer L plus 1 and multiply this with the derivative of S on layer L plus 1 with respect to S on layer L, and we need to sum this for all j's, j is running from 1 to n L plus 1. So again, this is just a simple application of the chain rule. A few slides ago, we proved that we can get SL plus 1 from other SL quantities with this expression. We also just proved that to calculate the delta L backpropagated error, then we just use its definition and then a chain rule, and then we know that this is how we can calculate the backpropagated error. It's very easy to see that the derivative of SJL plus 1 with respect to SIL using just this expression is nothing else, just this term here. And if you look at this quantity here, is just exactly the definition of the backpropagated error at layer L plus 1. Therefore, we proved that the backpropagated error indeed can be calculated recursively from the higher level layers. So for example, if we want to calculate the backpropagated error at layer L, then we can get this expression using the backpropagated errors at layer L plus 1. We are now almost done. We will use this recursion to calculate the derivative of the errors with respect to the weights of the neural network. We know that by definition, SL is just the summed inputs of layer L. With one more application of the chain rule, we can calculate finally the derivative of the squared errors with respect to the weights of the neural network. According to the chain rule, the derivative of epsilon squared with respect to WLIJ is just the derivative of the squared error with respect to delta SLI multiplied with the derivative of SLI with respect to the weights WLIJ. From this expression, it's very easy to see that the derivative of SLI with respect to the weights WLIJ is nothing else, just XLJK, And the first term here, the derivative of epsilon squared with respect to SLI, is just the negative backpropagated error at layer L by definition. So we got that the derivative of the squared error with respect to the weights WLIJ is just this expression here, where delta is the backpropagated error, and we need to multiply that by XLJ. So finally, we can show the gradient descent updates using this expression, and that is called the backpropagation algorithm. It says that WLIJ in the next iteration is just WLIJ in the current iteration plus mu learning rate times delta Li times XLJ. And here mu is just a positive learning rate, and we know that the delta quantities can be calculated recursively from the other deltas on the higher level layers. This is the basic form of backpropagation. There are many different versions of it. For example, sometimes instead of just calculating the derivative on one training instance, we calculate them on a mini batch of training instances and then add these derivatives together. We then use this aggregated gradient in the gradient descent algorithm. So that's called the mini batch version of gradient descent. We also often replace the gradient descent algorithm with something more sophisticated. For example, often we use an adaptive moment-based optimization method, which is the so-called ADAM algorithm. We will study these more sophisticated algorithms later. So this was a quick summary of the backpropagation algorithm. We will discuss some more applications, some more special cases later. But for now, thanks for your attention.